So in the last lecture, we were talking about an example which dealt with combined signal operations. And we looked at the time shifting operation, which involves delay or advance of a signal. Then we looked at a time scaling operation, which has the option of time shrinking and time expanding options, and then the flipping operation. And then we talked about a sequence of operations so that we have a structure to these combined operations. So the recommended sequence was first do the time shift, then do the time scale, then do the flipping. Of course, if you want to do it in a different way, there is no signal operations police that is going to come to catch you. All you have to do is keep track of. If you choose to do the flipping first, the delay will become an advance, right? So as long as you're keeping track of that change, you will be fine. This is only the recommended sequence of combined operations so that there is some sort of a structure to the three operations combined. And there have been some homework problems assigned to get you some practice on this. Now, continuing on that same example, continuing on that same theme of combined operations, we'll do one quick example over here where we are given some function of time as 3t minus 4, but it is only 3t minus 4, which is a line with a slope of 3 and a y-intercept of -4, but it is only that between 2 and 3. And at all the other times, it is 0. And we are asked to compute another function of time g of t, which is related to f of t using this function, f of t divided by 2 minus 3. So how can I do that numerically? My goal is to just express g of t in bracket notation over here. So let's see, g of t, I can express g of t given to me as f of t divided by 2 minus 3. So instead of t, the variable t, I'm going to substitute t divided by 2 minus 3. So this is going to be expressed in bracket notation. Over here I have 3t minus 4. So instead of t, I will put t divided by 2 minus 3. And that is only for that guy right there. And then I have minus 4, of course. This is going to be for 2 less than t divided by 2 minus 3 less than 3. And then, of course, it's going to be 0 otherwise. Now, as you can see here, if you look at the range of time for which this is a line, I have it in a slightly weird form over here. 2 less than t divided by 2 minus 3 less than 3. So I would want it to be expressed as just a range on t variable. So to convert this to t, what would I have to do? I would have to add 3 everywhere and then multiply by 2 everywhere. So if I add 3 here, here, and here, followed by multiplication of 2 here, here, and here, I will get the function in this form. I will get g of t to be, let's see, it's still going to be 3t divided by 2, and then you have -9, -4, so -13, and then 0 over here. For the first one, it is going to be 2 times 2 plus 3, that is 5, times 2, 10, less than t, less than, let's see, 3 plus 3, 6, times 3, 12. And this is going to be otherwise. So just a quick example to go from one function to the other, and that will give us that. All right, there's a question. Somebody raised their hand. You mean multiply by 2 on that last one? Yes, I did. Thank you for catching that. Other questions about this example? So expressing one function as a different function, however, keeping track of the range on the time variable. Okay. Now that was the last example on lecture 2 that I had missed. So let's move on to lecture 3 here. That's our agenda for today. So we'll begin with talking about unit step function, and you guys have already talked about unit step. We have seen unit step before. However, now we are moving into a slightly strict definition of unit step. We are not taking any discontinuity in the unit step for granted. So for example, if you look at the unit step, it is going to be 0 for time less than 0, and for time greater than 0, it is going to be 1. But as you can see over here, at 0, there is a discontinuity going from 0 to 1 in a very, very short duration of time instantly. That indicates that it is simply a theoretical discussion on unit step. It's not a practical one, because practically nothing can instantaneously change levels. So on purpose, just to deal with a unit step on a very mathematically strict sense, we are going to leave out time equals 0 over here. At time equals 0, there is a discontinuity in the unit step. I heard someone speak. Is there a question here? All right, let's move on. Now, if that is the unit step and its corresponding bracket notation on the right, what would happen if you scaled the unit step by some real value alpha? In this case, the way it is shown, alpha is a positive number, but it could also flip downwards. So alpha could also be real and negative. Negative. So if alpha is, say, some alpha is some real number, then the height of that unit, it's not going to be unit step anymore. It is going to be a step of alpha units. So the y value, the y value is going to be alpha. So it's going to be 0 for time less than 0. However, when it goes for time greater than 0, it's going to be having a value of alpha. So that's alpha u of t. So 5 u of t, 10 u of t, for example. So all you're doing is increasing in the amplitude, the strength of the signal. So that's your unit step being dealt with in a very strict mathematical sense. Now, how do you represent signals in terms of step function? So I want to deal with it in a very, very generic sense. So what I'm going to do is I'm going to start with an arbitrary function of time, f of t. My horizontal axis is time. My vertical axis is f of t, the function of time. I have over here a pulse like looking waveform. The pulse is turned on at a, time a, and the pulse turns off at b. So it's 0 for time less than a and greater than b, and it is value of m, some real number, between a and b, time a and b. At a, there is a discontinuity. At b, there is another discontinuity. So how do I express f of t in the terms of step functions or u of t's? The first thing that I would do is I would consider m u of t minus a. So all I'm doing is I am doing a time shift operation on the unit step by a factor of a. So I'm moving things to the right by a because I want this gate to open at a. I'm also scaling my unit step by m. So the height has become m over here. And then in the next piece, I am subtracting m u of t minus b. And the sketch of for that is negative m, so it's flipped downwards. And it's also a time shift of b. So it's moved to the right, and it's instead of starting at 0, it is starting at b. And it is flipped on down because it is a negative m for the amplitude. Now, if I add these two now, because I've already incorporated the negative sign here, I just need to add there. If I add them now, what do I get? I get my signal f of t, which can be mathematically represented as that. M is the height, u of t minus a minus u of t minus b. So you can express this very quickly by keeping a track of a and b and a and b. And of course, you also have to do the m. So that's one quick way of representing signals in the form of u of t's in step functions. Now, how about if the signal is not very straightforward, meaning it is not directly a manipulation of u of t? You actually have to uh, change a few things about that function. So in this case, we are still trying to represent signals in terms of step function u of t's. Our time axis is the horizontal axis. Our f of t, the function that we are trying to represent with step functions, is f of t, which is the horizontal axis. And the signal has changed a little bit. Below a, and we are assuming that a is greater than 0, b is greater than a, c is greater than b, and c is a finite number less than infinity. And we are also assuming, to keep things simple, that m is a value that is real and positive. Between, less than a, less than t equals a, you have f of t as 0. Between a and b, it is a line increasing with a slope. And because we know these values of a, b, and cap m, we can find out the equation of that line. And between b and c, it is actually going down with a negative slope. So if you know b and c and cap m, you know the equation of that line as well. So f of t can be expressed in bracket notation by using the two concepts. One is equation of the line and the fact that we know m, a, b, and c. So, let me quickly show you how to do the one of them. I'm sure you guys know this already. Say, for example, I wanted to do between time a and b, right? So this is when f of t increases between a and b. I would need two things. One is the slope and the y-intercept. And y-intercept can be obtained by using the 2 points on the line. Those 2 points can be a comma 0, b comma m, and you can find the equation of the line as well. And just to clarify, how do you find the slope? Slope is dy dx, dy divided by dx. So over here it's m divided by b minus a. So that's how you get the slope piece over there. And then it is that is essentially the y-intercept of that line. Similarly, you will write down the f of t between time b and c using another equation of the line. So slope and y-intercept and so on. That's between b and c, and it is 0 otherwise. So all the other places it is 0. So by using the fact that we know how to find the equation of a line, slope and y-intercept, we have expressed f of t in a bracket notation. Then we try to multiply those specific equations of the line with two different gate functions. Because this is one line and this is another line, I'm going to use one gate function for the increasing line where it doesn't change. There is one equation, and then one different gate for the line going down. So I need something that turns on at A and turns off at B. So that's that, u of t minus A minus u of t minus B with a height of 1. So there is no scaling there, it's just unit steps. Similarly, for the line going down, I have another gate which is u of t minus B minus u of t minus C. Open at B, close at C, and still the amplitude is 1. So all I would have to do to express f of t using the unit steps is by multiplying f1 of t, that is shown in red, with u of t minus a minus u of t minus b, the first term, and then for the second term I'm going to highlight in blue, or it is written up in green there. What is that? That is f of f2 of t, which is essentially the thing that is boxed in green, slope going down, multiplied by the gate function starts at b and stops at c. So those two combined, I have expressed f of t using step functions. Yes. So at A, B, and C, it is well defined. So you can plug in time equals A, it you will get 0. Time equals B, it anytime you get M. Time equals C, in any of these you get a 0. All right, let's move on here. Let's look at a gate function. Gate function is denoted using g of t. The sketch for it is shown over here. It is on for one time unit with a height of 1. In bracket notation, it is expressed as 0 for all the other times except for time between 0 and 1, where it is actually 1. There are also two discontinuities over here in gate function. A quick conversion between gate function and unit step functions is this. If you wanted to express g of t in terms of unit step functions, you need something that opens at 0 and it closes at 1. So that would simply be u of t minus u of t minus 1. That is how you can quickly express g of t, the gate function, in terms of unit step functions. Now let's deal with a general case. Here you have f of t. I'm trying to express this f of t in terms of gate functions now. Earlier we used unit step functions. Now I'm focusing on a gate function, g of t. So how do I do that? I'm using the same example here. So something that turns on at A, turns off at B, has a height of M. So it's the same f of t as before. So you start with g of t. So it is for one time unit, height is 1. Otherwise it is 0. First, you realize that the pulse width is 1. I need b minus a. So I would have to scale this or time scale this by a factor of 1 divided by b minus a. So I need to stretch it by a factor of 1 divided by b minus a. So if I did that, what would happen? Well, 0 will remain 0. 1 will become b minus a. The height, because I also need to do a m here. I'm also multiplying by a factor of m and I'm adjusting the height of that as well. So I've done a time scaling first. Then I need this f of t to be moved to the right by a time units. So I'm going to do a time shift by a. Essentially, I'm doing a delay or move to the right by a time units. So when I move this to the right by a time units, 0 will become a, b minus a will become b. The height m will remain as is. Now, how do I express that as the f of t? It will be as is mg of t divided by b minus a only after the time scaling. However, because I'm doing shift after the scale, you see we put a minus a along with the t. Now this goes back to the conversation we have been having about the combined time signal operations. If you did the shift before that, it would be separate from the time function. But because we did shift at the end, it would be included in the t minus a factor. So it's t minus a divided by b minus a. That would be how you go from g, the gate function, and express f of t in terms of gate functions. There is an adjustment of the time scale, there is an adjustment of the time delay, and there is also an adjustment on the amplitude, m. All right, I hope that was helpful. Let's move on to the next one. The integration and the derivative of step functions. Now, I hope that there are some alarm bells going on in your head, because we have already said there is a discontinuity in step function, and derivating it should not be a differentiable function. So there is going to be a problem, which is why we need to address it. So u of t, which is the step function that we are considering, again 0 1, time less than 0 it is 0, time greater than 1, time greater than 0 it is 1. It is sketched up over here. Now observe that as you integrate, so let's do the integral first because it's easier. As you integrate u of t function from left to right, you are essentially accumulating more and more area, and you are accumulating that area linearly, which is very critical. You see, if you integrate 1, you get x. Well, in this case, you are integrating 1 with respect to time. When you do that, you get t. So it's the constant becomes linear function t. If it was a triangle, then it would be t integrated will become t squared divided by 2, of course. But I want you guys to keep track of that. Only because it is a line, that's why when you integrate it, it will become a ramp function. If you start out with a ramp function and you integrate, you will get a quadratic and so on. So let's see. We are coming back to the question of what happens when you integrate the step function. When you integrate the step function from minus infinity to some stopping time t, you are expressing u of t as u of tau d tau. As long as t is less than 0, it is going to be 0. As you can see, when you are here, you don't accumulate any area. And as you go t greater than 0, as you move in, your area that you accumulate will be positive, and it will be linearly increasing with a slope of 1. That, by definition, is the ramp function r of t. So if we can say that integration of a unit step is a ramp function, consequently, the derivative of a ramp function should give you a unit function. So that's a identity that we are going to keep track of. So essentially, if I differentiate this guy, ramp function, I get back this. And it's very easy to figure that out, right? 0 differentiate 0. A line differentiate, you get the slope of the line, which is 1. All right, so integral, I hope you guys are comfortable with that. Let's move on to the derivative of u of t, which is slightly confusing. And it is confusing because of one reason. The reason is u of t is discontinuous. So if u of t is discontinuous, as you can see, there's a discontinuity at 0 here. So what is going to happen when we try to differentiate it? Well, strictly speaking, it is not differentiable because that's going to lead to an infinite slope. So informally, what we are going to do is we are going to introduce another function. We will consider a function delta sub epsilon of t, which is defined in its bracket notation as 0 for time less than 0. Let me show you both at the same time. This is 0 for time less than 0. So that's that. It is 1 over epsilon for time less between 0 and epsilon. So that's that. And when it is greater than epsilon, let me use the blue set. When it is greater than epsilon, you still get back the 0. So between 0 and epsilon, it is 1 over epsilon. And we are choosing those limits in to make sure that the area of this is unity, 1. And you will see why that is useful later on. So we are introducing this function delta sub epsilon of t, some gate function like function here. Let's start integrating this function. So now consider integrating delta sub epsilon of t. When you integrate this function, what happens? So work with me over here. I'm going to erase these 3 things, and I'm going to slightly move from left to right. 0, 0, 0, 0, 0, 0, 0, 0, 0. And then between 0 and epsilon, the area is going to increase. And it will increase to what? It will increase to 1 because the area of the total rectangle over here is 1. And after that, when you move to the right of epsilon, it will stay at 1. So something that is 0 for time less than 0, something that increases to 1 between time 0 and epsilon, and something that stays at 1 after t is greater than epsilon. So that's what happens when you integrate that delta sub epsilon from negative infinity to some arbitrary stopping time tau. T. The function we are expressing as delta sub epsilon of tau d tau. By the way, what is delta sub epsilon of tau d tau? All you have to do is this becomes tau, that becomes tau, right? Like there's nothing different. That is tau, that is tau. It remains the same. So, and then we are integrating with respect to tau. Just go back to the definition here, t and t. Okay, so we talked about how the result should look like. When you integrate delta sub epsilon of t from negative infinity to time t, it should go be 0 and then increase linearly to 1 and stay at 1. We talked about this. And we can now express that integration of delta sub epsilon in bracket notation. 0 for time less than 0, t over epsilon between 0 and epsilon, and 1 when t is greater than epsilon. You're absolutely correct, Alan. Now observe that as you find the limit as epsilon tends to 0, push this over here, what do you get? You get a unit step. So observe that as epsilon tends to 0, this particular function, integration of delta sub epsilon, will become u of t. It will be 0 and then it will be 1. That is your u of t. Therefore, we can define the derivative of u of t with respect to time as limit epsilon tends to 0 delta sub epsilon of t. And it is just epsilon because we are trying to differentiate. So if this becomes this, you differentiate this, you differentiate this. When you differentiate this, you get delta sub epsilon. You differentiate this, you get the left-hand side over here. Limit delta tends to 0, delta sub epsilon of t is defined as the direct delta function, or simply the delta function, or we are going to call that an impulse function. How does it look like as epsilon tends to 0? Delta sub epsilon, right? Like how does it look like? Delta of t, the impulse function, we are defining it as delta sub epsilon with epsilon tends to 0. So the question is, how does it look like? If we go back to the definition, this should be close to 0, right? Epsilon should move left. So very, very short duration of time. How about the height? The height of this is going to be tending to infinity, right? So the height of this is infinity. The width of this is tending to 0. That is your impulse function or delta function. So that's another identity that we are going to box over here. Maybe a better box. So all of this manipulation was done so that we can find our way to an impulse function delta of t. You will see this function delta of t many times over the course of this summer semester for this class. Delta of t, the impulse function. All right, questions about this derivative of u of t? All right, let's move on. A few things to note over here about the impulse function or the delta function. First, how does it look like? It looks like that. Our x-axis is time. Delta function is 0 for time less than 0 and greater than 0. And when it equals 0, it shoots up to infinity. That's why the direction is pointing up. There are very, very crucial things about this sketch that we need to address. Specifically, the difference between height and area, also called as the weight of the impulse. So the height of this delta function is actually infinity. However, the area under this curve, let me highlight that in blue here. When you integrate over the delta function, the area, which is also called the weight of the impulse, is 1. So unit area, how do I know that? Well, from before, you remember 1 over epsilon multiplied by epsilon, that was giving you 1. So the area is 1, however, the height is infinity. So we don't talk about height, we leave that as is. In our notation, all we do is we point out the area or the weight of the impulses by writing 1 or 2 or 3 or whatever beside that arrow pointing up. So this is what you will mention. All right, let's look at some properties. Delta of t is 0 for any time other than 0. The area under the function is 1. We talked about that. That is, for as long as we are integrating over that impulse, you will get a 1. If you don't integrate over that, then you don't get any area. So for example, if you want to sketch up that impulse at a time t sub 0, and notice that we have taken that impulse delta of t, we have done a time delay by t0, moved it to the right by some time t0, and we have also scaled it by some value alpha. So if you don't scale it by alpha, the area under that will be 1. So if you integrate over that impulse, it will be 1. If you have a scaling of alpha, which means it is alpha delta of t minus t0, then that scaling will become alpha instead of 1. So the area under that is going to be alpha now, so because the height has increased to alpha over epsilon, the x is also just epsilon, so this becomes alpha. Now to write it formally, we are trying to find the area under the function. So we express that as this: area under delta of t when you are integrating between a and b, as long as a is less than b. If a is less than b, you could have a and b over here, or you could have a and b over here, anywhere. But for example, if you are over here, let me draw it over here and here. If you are over here for A and you are here for B and you are integrating from A and B, then the impulse is being integrated over and you will get a 1. If there is no time shift, t0 is 0, that's what we have over here, then that particular value will be 0. Otherwise, it will be t0. The bottom line is, if you are integrating over the impulse, you get a non-zero area or non-zero weight. If you integrate, so for example, you have this is delta of t and this is t, this is 0. If a is greater than 0 and or b is less than 0, what do you have? A is over here, and if a is less than b, that means b is here, Or you could have b less than 0, that means b is here, that means a is here. In both those cases, you are not integrating over the impulse because impulse is right here, and you get a zero area. So I hope the properties of the delta function, at least the ones that we have discussed about the area, are clear. Let's move on here. Oh, go ahead. Is there a question? No. Well, let's try to do a simple exercise here. Sketch 5 delta of t minus 3. Let's try to sketch that. What do you have? We have an x-axis, we have a y-axis, then we have time. This is going to be t. This is going to be 5 delta of t minus 3. It is going to be located at what time? The impulse is going to be located at 3, pointing up with a weight of 5. So at 3, with a weight of 5. So that means that the impulse is going to infinity, the height is infinity. However, the area under that impulse is 5. So that's what we write explicitly. And at all the other times, it is 0, of course. Let me draw it a little bit bigger. All right, let's move on. Next, this impulse function is crucial to the sampling property, because all we have to do in order to sample a signal is to multiply a continuous signal with an impulse function that is located at that time. So for example, if we go back to this previous example, if I have some arbitrary signal, I will draw that in blue, and I multiply this with this function. So this is, say, x of t. If I did x of t multiplied by 5 delta of t minus 3, what do I get? I have increased the amplitude of that particular sample by 5 times, and I have actually picked out x of 3, because only at that time I'm going to get a non-zero value. All the others are going to cancel out because they're all 0. And then 5x of 3, I will also have a delta of t minus 3 that remains. So that will become my amplitude, and that will still be there. So eventually what I get is, I will get an impulse function with a height, not a height, the weight as 5x of 3 located at time 3. And if I did that for all the others, I would have essentially sampled the signal x of t, this is how the impulse function relates to the concept of sampling, which is essential to convert an analog signal to a digital one, discrete one. You need to be able to sample the signal. What does that mean? That means we are going to essentially select limited number of values in the signal as opposed to expressing all the values of the signal. All right, more about sampling later. Right now we are just looking at the sampling property. Now notice that the given signal x of t, it is sketched up in black over here. That's our continuous time signal x of t. We are multiplying the signal x of t with the delta sub epsilon function that we have defined, which is essentially this function in red. It is on for time 0 to epsilon, and it is having the height of 1 over epsilon. So if we take this x of t and you multiply it with delta sub epsilon of tau d tau, and you integrate from negative infinity to infinity, that means you're integrating for all the time. What do you get? That essentially gives us the average of x of t in the interval 0 comma epsilon. Think of it like this. What is the when you think about average, what do you think of? Add up all the numbers and divide it by the number of numbers. Okay, so how about this? What is that? It is still integration negative infinity to infinity. X of tau is x of tau. What is delta sub epsilon of tau? Delta sub epsilon of tau is only 1 over epsilon, but it is only that between 0 and epsilon. Let me make this tau instead. So that's essentially what this statement says. And it is the average, right? It is the average between 0 and epsilon. Why? Because you are adding up all the numbers between 0 and epsilon and dividing it by the number of numbers, epsilon. So that's how this function, you can think of this statement. All right, let's go ahead. Now consider if we are truly looking at sampling, we would want this width of this red rectangle to tend to 0. So as epsilon tends to 0, we are going to interpret that integration of x of tau delta of tau d tau as one value, that is your x of 0. That's essentially the sample or evaluation of that function x of t at time 0. And you're getting that time 0 because the impulse delta is valid at that time 0. For other values, x of 1, x of 2, x of 3, and so on, you would have to have a shifted impulse function, delta of 1, delta of 2, delta of 3, and so on. Sorry, delta of t minus 1, delta of t minus 2, and so on. All right, let's go a little bit deeper here. We can also see that for any two signals, x of t and y of t, if we have a situation such that x of 0 is equal to y of 0, which means that when you evaluate the function x at time 0, it is the same as evaluating y at time 0. At other times they might be different, but at time 0, if they happen to be the same, then we can say that x of t multiplied by delta of t, the continuous time signal multiplied by the impulse function, is the same as for y of t multiplied by delta of t. So you can think of it graphically as this. Imagine that you have, let's say we have black here, this is still time, that is some functions that are plotted together. In red, I'm going to do this, and in blue, I will do this, right? And I have this as my y of t, and this is my x of t, for example. So no matter what they are at other times, if they are the same, let me move these two to 0 because right now we are talking about 0. If they are the same at the point of interest, which in this case is that right there, then that's how we are saying, right? X of 0 is the same as y of 0. If that is the case, that means that even though at other places they are not equal, we can say x of t multiplied by delta of t is the same as y of t multiplied by delta of t. It's like the red one multiplied by the impulse at 0 is the same as blue one multiplied by the impulse at 0. That's what this statement means. Next, all the properties that were discussed before, They will hold true even when the impulse is shifted. So for example, over here, we were talking about 0, right? And we could apply the same thing if we shifted the entire thing somewhere else. And we looked at, you know, an impulse located at that location, t0, some t0, and you could apply the same logic. And the corresponding statements for that would be, when you integrate for all time, you multiply x of tau with an impulse at tau sub 0, you will essentially evaluate the function at tau 0. We will do some examples about this to get some more clarity. Remember, this is only when you integrate. So we'll also have to worry about what happens without that integration. What happens when you just multiply those two? So we'll do more examples in just a bit. And to continue with this theme of comparing the two signals x and y, if x of t0, which is the sample of x of t at time t0, if it happens to be the same as y of t0, then we can say x of t multiplied by the impulse at t0 is the same as y of t multiplied by the impulse at t0. That statement can graphically be viewed as what we just discussed here, moving, let's see, not this, moving the functions to the right. So those two are still x of t and y of t, but instead of looking at uh, delta of t, now we are looking at delta of t minus some tau 0, if that is tau 0. All right, questions about the sampling property. So sampling property is right there, boxed in red. If you take a signal x, you multiply it with an impulse located at some arbitrary time tau 0, and you integrate over that tau 0, then you will evaluate the sample of x at tau 0. All right, let's do some examples here. We talked about this. Let's see. One second here. All right. So the sampling property, you had an integration. After you multiply the continuous time signal with the impulse, you had an integration for all time, negative infinity to infinity. So that's when you evaluated the value of that signal at that particular time where the impulse was active. How about if there is no integration? So how about just the product of x of t with delta of t minus t0? So to illustrate this, we have the sketches on the left. There is a x of t, there is a delta function that is shifted by t0, and then there is a product that we are sketching. X of t is some arbitrary continuous time function. In this case, we are highlighting t sub 0, and at t sub 0, x of t should simply be x of t0. When you multiply before you multiply, let's plot them individually. So we have sketched x of t right here, and we are sketching now delta of t minus t0 over here, which is essentially an impulse that is shifted right by t0, assuming t0 is positive. If it is negative, then you are advancing the signal, but you already know that. Now when you multiply these two, what is going to happen? For all the other times, so you see, for all these times less than t0 and greater than t0, it is going to evaluate to a 0. Nothing there. However, at t0, you are going to multiply x of t with x delta of t0. So you are going to have to evaluate x of t at t0. So the area, the weight of this impulse you are going to end up with will be x of t0, which is essentially that value right there. But it will continue to be an impulse at t0. So we cannot simply write x of t0, we have to include delta of t minus t0, which is often missed, which is a common mistake, right? I've seen a lot of students represent this product over here as simply x of t0. No, when you integrate, yes, you get x of t0, which is the sampling property before. But if you're not integrating, then you still have to include delta of t minus t0. It's still an impulse after you multiply. So all you're doing is you have changed the weight of that impulse. Over here, the weight was 1. You have changed that weight to x of t0, which is that guy right there. Okay. There is another way of looking at it using the sampling property. What do you have? The sampling property says if you take the product of x of t, delta of t minus t0 dt, and you integrate, I only have delta of t minus t0 valid at t0, which means I only need to worry about x of t0. Other times it is 0. So x of t0, delta of t minus t0 dt remains as is. X of t0 right now is a constant, which is because it's a value. So that can be moved outside the integration because it's independent of time t. And then what we have inside the integration is negative infinity to infinity delta of t minus t0. We know that when you integrate over an impulse, you have to get a 1 because 1 over epsilon multiplied by epsilon, it gives you 1. So you get x of t0. So that was for the sampling. But when you don't integrate, you have to still include the delta of t minus t0 there. All right, so I hope that you see the clear distinction between multiplying a continuous time signal with an impulse function and multiplying an continuous time signal with an impulse function and then integrating for all time. Let's do some examples. The first example over here is t squared minus 9 multiplied by delta of t minus 4. So let me work out this in red. If I expand this, what do I have? I have t squared delta of t minus 4, so an impulse at time 4, minus 9 times delta of t minus 4. I can't do anything about this. This is as is. But I can do something about this. I can use the product rule that we just talked about right there. So I need to evaluate x of t0, and then I also have to have delta of t minus t0. So what would that be? That would be 4 squared delta of t minus 4 minus 9 delta of t minus 4. That's fine. And then what is that? 16, 9, 7. So that would be your answer. You can also view all of this graphically, right? So let me show you that graphically over here. Let's see. Still have this, still have that. I'm going to use, say, for example, I can use this. Let's suppose I'm trying to sketch all of this. T squared. I will sketch t squared first. What is t squared going to be? This is t. T squared will be a u, right? So let's see. This is going to mess things up, but I'm going to move this up a little bit. All right. So that's going to be your t squared. And where is the 9? 9 is essentially right here in red. 9 is there. Doesn't change with time. And where is the impulse? Impulse is at 4. So let me do this. Because at 4 it will be 16, so I wanted to show you that this is just an impulse at 4. So you're essentially multiplying, so only the critical values are just here, right? So you multiply the impulse with t squared, you get 16, because only evaluating at 4, right? So that's 16 minus uh, 9, that will be 7. And because you're multiplying this signal with an impulse, you will still have an impulse there and impulse there. So when you do multiplying, what you're getting is you're getting a first impulse of height 16 and you're subtracting another impulse of height 9 to get an impulse of height 7 at 4. I shouldn't say height, I should say weight. Height is infinity. So graphically you can view all of that like that. Okay, questions about this example? So let's see, wouldn't the impulse be to the right of the intersection between 9 and t squared? Uh, yeah, you're right. I just quickly drew this. So you're right, absolutely right. So all of this, if I were drawing everything to scale, all of this would have to, sorry, not that. So the intersection happens much faster, right? Because 9 is going to happen at 3. This is at 4. So you're absolutely right. This is actually happening after this. This is 4 because this is 3. Other questions? But the main takeaway from here is the fact that you are going to get two impulses, you subtract to get your answer here, which we have already expressed mathematically using 7 delta of t minus 4. All right, other questions? All right, another example here. We have integration for all time. We have a cosine function 2 pi t. We have an impulse at time 1 over 6, and you're integrating with respect to time. So this is essentially your sampling property. So using sampling property, let's just cite the sampling property here. Sampling property. We had integration x of tau delta of t, sorry, not t, tau minus tau 0 d tau equals x of tau 0. That was our sampling property. Evaluate the function at tau 0. That's it. So for this, if you apply the sampling property for this example, what do you get? We get cosine 2 pi, let's see, instead of t, I'm going to use 1 over 6. So what do you have? You have cosine pi over 3, which is half. So when you're integrating over that impulse, you get a value. When you're not integrating over that impulse, you get a impulse. Let's move on here. Let's now talk about differentiating step functions. Differentiating step functions, now that we have introduced the concept of an impulse, things are going to be much more simpler. So what we derived earlier is this. If you want to differentiate the unit step, all you have to do is, so let me just cite that. Let me just show you where we discussed this. When we were doing the derivative, okay, quite a bit back. Okay, so when we defined this, we said the integration of delta sub epsilon becomes u of t as epsilon tends to 0. So if you integrate both these terms that I'm going to highlight here, integrate this, differentiate this and differentiate this, that leads to that identity there as epsilon tends to 0. And we are taking this particular result and we are talking about the derivative of the unit step right here. So that's coming from there. So if you differentiate the unit step, that is essentially the limit epsilon tends to 0 of delta sub epsilon that we defined, which is the same as delta function, the impulse function. So if you have u of t, that's the sketch of u of t. If you go through a system that essentially differentiate with respect to time, the output of that is going to be an impulse function with a corresponding sketch. Now, to keep things simple, think of it in terms of slope. Slope is 0 here, slope is 0 here. So that's why it's 0 here and 0 here. Now, when you have a slope of infinity, that's when you get an impulse. But because you have u of t, the weight of that impulse is going to be 1. If you had 2 u of t, the weight of that impulse would be 2 delta of t. So 2 and so on. So you're literally keeping track of slope because you are differentiating step functions here. Now, what about derivative of u of t minus a? So now we are trying to do a time shift operation on a unit step and then still differentiate with respect to time. Now we can, because you have a function inside a function, one function is unit step and the function inside that is t minus a, we can use a chain rule for differentiation, which is differentiate u of f of t with respect to t, where u of t is one function, f of t is the function inside it. Using chain rule, you can write that as differentiate u of f of t divided by, with respect to f of t first, then multiply it with derivative of f of t with respect to time. In our case, we know that derivative of u of f of t divided by f of t is delta of f of t. How did we get there? Well, if you zoom in here, t is now f of t, f of t, f of t. And then the next term remains as is. This term is as is. So you've got an impulse function with the argument of f of t, but you're still doing a differentiation of, in this case, t minus a or f of t with respect to time, which should be very straightforward because it's just t minus a. All right. Now using this chain rule, we can move on to the next step. U of t minus a is, if I assume that a is a positive, then I'm moving it to the right. Otherwise, if a is negative, then I'll be advancing it, moving to the left. But in any case, this is how u of t minus a would look like, no matter where a is, positive or negative. If you want to differentiate this function with respect to time, based on the chain rule application we did just now, it would be delta of t minus a or delta of f of t, and then differentiate f of t, in this case t minus a, with respect to time. So that would be delta of t minus a, because derivative of t minus a with respect to time is simply 1. Delta of t minus a can be sketched as that. It is located at a with a weight of 1. And just so that you have clarity on this, if you had scaled this to 2 u of t minus a, then this would be 2 derivative of all of that, then this would be 2, this would be 2, and this would also be 2, which means that this would also be 2. So the weight of that will be 2. The location is still a. How can you view this intuitively? I'm moving from left to right. As I'm moving, I'm keeping track of the slope. 0 here, 0 here, I got that. At a, I have a discontinuity. When I differentiate that, I will get an impulse. How about differentiating u of minus t with respect to time? We can still apply the chain rule and get to this answer. So u of minus t is essentially a time flip. So you have taken unit step, you have flipped it with respect to the vertical axis, and you have got u of minus t. Differentiating u of minus t with respect to time will be delta of minus t. Delta of minus t and delta of t are the same because an impulse function is an even function. Differentiating minus t with respect to time is going to lead to negative 1. So that evaluates to negative delta of t. So this would be an impulse function pointing down with a weight of negative 1. Again, intuitively, if I'm moving from left to right, slope is 0, discontinuity, slope is 0. Discontinuity is from high to low or going down, so I'm going to be pointing down. In general, you can write this for u of minus t as derivative of u of minus t minus a with respect to dt is minus sign, because there is a minus there, because you had a minus there, and then in impulse at t minus a. So an impulse that points down with a weight of negative 1. Again, if you had this as 2, this would be 2, this would be 2, this would be, everything would go to 2, right? All right, I hope this is clear. Let's move on to the next one. Now here I want to sketch derivative of this particular function x of t, and because we have the necessary background, let us try to do this in one step as opposed to doing this one step after the other. Let's just try to do it in one go, and please feel free to ask me questions as I'm doing this. What I'm going to do is I'm going to first sketch out. I'm doing a sketch, right? So I'm doing a sketch. I'm going to do this as x-axis and y-axis. I have time here. I have derivative of x of t with respect to time here, right? And I will sketch the derivative in red. So what do I have for time less than 0? For time less than 0, the slope of x is 0. How about time greater than 3? For time greater than 3, the slope is also 0. All right. So less than 0 and greater than 3 is 0, right? So let's see. Go there and then 0 there. And then let's say 1, 2, and 3. And then after that it is 0 here as well. Okay. So I got the 0 piece, which is good news. This is 0. I'm saying this is 1. This is 2. Oh, come on. This is 3. This is 4, and so on. Okay, so what would happen between 0 and 2? Well, between 0 and 2, the slope of x of t is positive, and dy by dx is 2 divided by 2, so 1. So the slope is 1. So derivative of x of t should simply be 1 at that time. So let's say this is 1, 2, 3, and so on. So between 0 and 2, the it would jump and right. Next, between 2 and 3, first I have a discontinuity at 2. How is it going from high to low or low to high? Well, it is jumping down, right? As I'm sketching from left to right, that is going from 2 to -3. So that means it is a jump going down by 5 units. So that would correspond to an impulse with a weight of, oh, by the way, this is going up to 2, right? So I can extend this even here until here. And at 2, I'm going to get an impulse pointing down. Weight would be -5. That's because of the discontinuity. Let me move this 2 a little bit to the right so that you guys can see it. Okay, so that's as far as discontinuity is concerned. How about between 2 and 3? I have a line moving up, so it's the slope is positive. And how is the slope going? I only need the slope. I don't even need the y-intercept. The slope is what? Change in y is 3, change in x is 1, so the slope is 3, positive 3. Okay, so that would give me red positive 3, so that will jump up here and then it will stay that until 3 and come down. All right. So that would be that's the complete answer. Questions about this example? All right. Now let's try to find the equation of so it's the same problem, but I'm trying to reach to that same answer, hopefully the same answer, but with equations. So a little bit more math heavy route to reach to the same answer. So I want you to be aware of multiple options here, which is why we are doing this. Same example, but here we are trying to find the equation for derivative of x of t. So what I'm going to do is I'm going to express x of t in the form of unit steps first. So for time less than 0, it is 0. So I don't even have to worry about that. But between 0 and 2, x of t is a line going up with a slope of, let me write this down, with a slope of 1 and a y-intercept of 0. So that equation is t. That's between 0 and 2. How about over here? Between 2 and 3. We found out that the slope was positive, 3t. How about the y-intercept? The y-intercept of this line. Well, the way I like to do is, if I keep moving backwards, from 3 to 2, it went from 0 to -3. From 2 to 1, it will reach -6. From 1 to 0, it will reach -9. So 3t minus 9. That will be the y-intercept here. So now we got equation of the individual pieces of x of t. all we need to do is multiply those uh, linear functions with their corresponding gate functions. So open the gate at 0 and close the gate at 2 for this guy, and then open the gate at 2 and close the gate at 3 for this guy, and then we are done. So let's do that. X of t is, it is going to be t between 0 and 2. So u of t minus u of t minus 2. And then we have 3t minus 9 between 2 and 3. So let's do that. We have plus 3t minus 9 multiplied by u of t minus 2 minus u of t minus 3. That's it. I've expressed x of t in the form of unit steps. Now I notice that there is a u of t, there is a u of t minus 2 here and here, there is a u of t minus 3. So I can combine the terms for u of t minus 2, u of t minus 3. So let's do that. I have for u of t, I can just leave it as is, tu of t, plus for u of t minus 2, I have 3t from here minus t from there. So I have 2t and minus 9. U of t minus 2. All right, next 2 minus 2 is done. I have u of t minus 3. For u of t minus 3, it's just that one term. So negative 3t minus 9 u of t minus 3. Done. Now let's differentiate dx of t divided by dt. So derivative of x of t with respect to time. So what do I have? T u of t, first term, product rule of differentiation, f prime g plus g prime f. Differentiate t, you get 1. Leave u of t as is. Differentiate u of t, you get delta of t. Leave t as is. I hope you guys are following along over here. Next, let's highlight this in a different color here, maybe pink. Same strategy. 2t minus 9 multiplied by u of t minus 2. So when I differentiate 2t minus 9, I get 2 u of t minus 2. And I have plus. Then I differentiate u of t minus 2, I get delta of t minus 2. 2t minus 9 remains as is. All of that is going to be in pink. Next, I have, let's see here, the third term, maybe I highlight in yellow, is going to be what? Negative. I want to differentiate 3t minus 9, so I get 3 u of t minus 3. Then I have negative 3t minus 9 delta of t minus 3. All right, so I hope you guys are doing okay so far. I'm going to highlight all of that in yellow for the corresponding term there. Next is applying the properties that we have learned. Delta t multiplied by delta of t. So what is that going to be? Evaluating the function t at time 0. So this guy is going to be, let's see, 0. And what do you have here? 2t minus 9 delta of t minus 2. So what do you have here? I need to evaluate this at time 2. So 10 minus 9, uh, so this would be what? Negative 4, negative, no, 4 minus 9, negative 5, delta of t minus 2. And then another delta function that I need to evaluate is right here. So for this one, I need to evaluate the function at 3. So that would be, in fact, I'm just going to do this for that. I'm going to leave out the minus sign up front as is. 9t minus 9, so that's 0, gone. Right. So it's 0 delta of t minus 3, which is 0. Similarly, over here it is 0 times delta of t, which is 0. All right. So I hope you guys were okay with those little simplifications there. Let's continue with our proof here. So this one, it will be u of t will be as is, 0 there, 2 u of t minus 2 is going to be remain. What else? Minus 5 delta of t minus 2 remains. What else? Minus 3 u of t minus 3 remains. All right. And that's it. U of t plus 2u of minus t minus 2 minus 3 u of t minus 3, and then an impulse function with a weight of negative 5 at 2. Now, if you look at this and try to relate that to the sketch that we have drawn, it is exactly the same sketch. And at a later time, if you guys want to sketch this and match things up to the one that is earlier, you can do that. So my claim right now is that it will match the sketch. All right, questions about this example. So what we did is we did two things, right? In this one, we used the product rule of differentiation, and the other thing that we used was when we had a function multiplied by an impulse, we evaluated the function wherever the impulse was active, and because there was just a multiplication of those two, we preserved that impulse at that location, and then we just manipulated, went through some algebra to combine common terms. Questions here? All right, let's move on. Now let's talk about the time scaling of delta functions. We have about 5 minutes left. Let me get through as much as I can. This is not that difficult now that we have defined delta sub epsilon. So the way we defined that delta sub epsilon of t, which helped us to differentiate the unit step, was a width of epsilon and a height of 1 over epsilon, such that our area under the curve is 1. And we use that to come up with this relationship, with this result. Limit epsilon tends to infinity, delta sub epsilon of t will equal delta of t, the impulse function. So this epsilon will move left as close to 0 as possible, and then the height of that will tend to infinity. The area under it will continue to be 1. Now, what happens when you do a time scale of this delta function? Specifically, what happens when you do delta sub epsilon of alpha t? You are scaling that time by alpha. So we know that when you scale things by alpha, it will do a time scale by epsilon divided by alpha. So this point epsilon will become epsilon divided by alpha. 0 divided by alpha will continue to be 0. So that will not change. This is using the time scaling operation, signal operation. The height remains as is, 1 over epsilon, 1 over epsilon. We just changed the width. Now, because we changed the width, we essentially changed the area as well. Now, our area is 1 over epsilon multiplied by epsilon over a, which is 1 over epsilon. Now, because of that little change here, our delta of alpha t is limit epsilon tends to 0, delta sub epsilon of alpha t. We have scaled the signal alpha here, we have scaled the signal alpha here. So essentially it's saying, you can look at it in this way. Substitute some new value alpha t instead of t. You get that identity from there to there. And graphically, that is the change that we'll have to make. Now, area of 1 over alpha is not so good. Mathematically, it's not very convenient. The reason is it is not following the property of an impulse function. The property of an impulse function is when you integrate over it, you should get an area of 1. So in order to get an area of 1, what we can do is we can do an amplitude scaling on top of the time scaling. And we are going to scale the amplitude by absolute of alpha because we don't want that to become negative. Now, absolute of alpha, delta sub epsilon of alpha t. So the time scaled version of delta of epsilon of t that was before, we have just scaled the amplitude by absolute of alpha, which means our 1 over epsilon now becomes absolute of alpha over epsilon. Our time limits will remain the same, 0 and epsilon over alpha. But our area has changed from 1 over alpha to 1 because we have increased it by a factor of absolute of alpha. Now, because we have multiplied it by absolute of alpha, all we are going to do is multiply both sides over here by alpha and alpha. Let me erase this so that there's no confusion later on. So you get absolute of alpha there and absolute of alpha there. Now, based on this, you can compare what you have over here, absolute of alpha delta of t, with what you have over here, delta of t. And the reason why you can compare them is because area of under the curve is 1 over here as well as over here. So you can write this particular statement because of that. Once you write that, you take this absolute of alpha to the right side. What do you have? The time scaled version of an impulse is delta of t, but you also have to divide it by an alpha. So that is not very straightforward. Many students might think that when you do a time scaling of an impulse function, it should be an impulse function, it shouldn't change. However, you have to incorporate the scaling of the area. The area goes down by a factor of 1 over absolute of alpha. So that's to be taken care of. All right. It is 12:04 right now. Let us stop here for today. And then we will continue our discussion on signals and systems on Thursday morning. I will stop recording now.